Anyway, so today I'll be talking about billet inspection. And my name is Gavin Dow. I'm with a company called AOS TPAC, and I'll explain a little bit about what we do. And actually, I'd like to invite you to our booth. You can't miss it. It's the one with the big balloon when you walk in. Okay, so billet inspection, for maybe some of you are very familiar with this application, maybe some of you are not. So just to provide a little bit of background, so basically with billet inspection, what we're speaking about is for the aerospace industry, which common materials are titanium or nickel. There are some more nuanced alloys of that, but I'll just refer to it as Ti64 or titanium in general. And then so right now, the current NDT inspection procedures are typically based on a conventional UT type of technique, and even there, that's quite nuanced depending on who the manufacturer is. But the idea is with current innovations in what we do in terms of the electronics, so we make ultrasound equipment, and also the imaging techniques that go with the equipment. So in a combination of the phased array or full matrix capture that you hear about nowadays, or even adaptive techniques, and then even phase coherence. So there's lots of techniques that have been introduced thanks to this concept of the full matrix capture type way to acquire data. So let's see how we can use that in this application to do things like improve signal to noise ratio, improve sensitivity, and then the best part is faster inspections, because time is money. And so a lot of times, not just to get the better result, but can we do it faster even? So we don't have to lose one for the other is the idea. So right there on the bottom of the slide, okay, so we have the billets, that then those billets are cut into smaller pieces that go into the forgings. Some people might refer to that as a sonic shape forging. It's an intermediate stage for the disc to be inspected before the final machining, and then to go into the airplane that we all rode to get here. Well, maybe some of you didn't. So this is very important to our safety. Okay, so this material is known to be, at least in titanium, it's known to be noisy in a sense. We heard a very good discussion earlier on noise. So you could see here, and I want to thank Dr. Turner, who's sitting in the back. Thank you for this slide to demonstrate the fact that we do. Here you could see the C scan, and then here, of course, everybody knows the A scan, and you can see this signal here is coming from noise. So this material being noisy, that is also posing a challenge to this application. Okay, so this is something that I'm sure everybody knows, but just to have a quick review of what, the terminology. Okay, I mentioned earlier, typically this application is conventional UT. You have phased array, which conventional UT, as a lot of you know, the limitation of that is it's slower because it takes more time. You depend a lot on the mechanical accuracy, a lot more. Then you have to depend on the mechanical movement of the angle. So there are some limitations there. Phased array brings a little bit better improvements in terms of, okay, well now we can phase in the sense of steer the angles, but still we could even do better with resolution, higher resolution. And not just higher resolution. A lot of times people think that when we move to this FMC, TFM-like technology, although you have higher resolution, you're going to lose on speed. But that's actually not the case. That I'll show in a little bit. And actually, I won't go too much into how we do FMC or plane wave imaging or these things. I actually have a talk at 5:20 today that will go in more detail of that. So this one is just to review the application. And I'm sure many of you have heard this many times. So this is basically a cross-section of a billet in this diagram. So you have element 1 to 128. That's a linear array. So what we would propose is to use a linear array. And then here in the next slide I'll show, but we marked each of the areas of where we would look at the data. And so you basically put the linear probe, rotate to get the volume of data. And so here you could see here, this is the the D scan, which is from this side, the B is on that part, and then the C from the top level as you rotate. And then you can see here that this is a number 2 flat bottom hole, and this is just the starter area. So when we were doing this was our first prototype of our setup with this roller. And then here we've upgraded since then to a little bit better system here. So here we have our roller. We have a turntable here for doing our R&D on forgings or on discs, anything that we could turn. And then here's a little zoom in of the roller. And then this is just, so we come from an instrument technology, right? So sometimes it's fun to see something moving, but maybe for you guys it's boring. For us, it was a little exciting to have this. Okay, so I'll go past that. Here, this is just to show, well, what do we do? You know, earlier I said our company is AOS TPAC. So AOS, what we do is OEM electronics. So we work with people that use our OEM electronics plus our software development kit to create their own solutions. And then inside our company called the Phase Array Company, what we do here is more solutions where we support our integrators. We provide solutions that integrators can then use for the final system. And then we do things like R&D on various applications. And so we have a software here we call Fastview that some of our customers can choose to use. If they don't want it, it's fine. They can use their own. But this software we've developed to support lots of different technology, like I showed before, phase array, FMC, conventional UT, various things. Even if you stop by our booth, even air-coupled UTs, it's quite versatile. And then so a lot of the experiments that we did for this application is using this device here, the Pioneer. And so this is just to tell a little bit about our Fastview software, in the sense that it's a very powerful software that's very flexible. You can choose the layouts of how you want to view your data, which is very important in NDT because, you know, everybody thinks sometimes from their point of view. Us as an instrument manufacturer, we talk with so many people in different industries. Maybe it could be from railroad, aerospace, or oil and gas. But everybody they think that UT should be the way they view it from their industry. But in fact, there's so many different ways to view the data, how the screen should be made. So this software is very flexible in a way to be able to customize that layout, customize the reporting, to be able to handle all the different aspects of NDT, specifically phase array. Okay, so now just to go back to what we're talking about with the billet. Okay, so in this case, what's interesting is, okay, we'll talk about productivity, meaning in terms of speed, to get the inspection speed. And so it's interesting here, if you use a linear probe, here this is just a simulation of the beam profile of the probe here using SIVA. And you can see quite nicely the coverage and the swath size, I'll refer to it, for that beam. And so you can cover a large area of that billet section instead of conventional UT where you would have to just one at a time, right? So that where this, here it's a lot smaller going down the billet as you rotate. So the advantage of here is larger coverage. Okay, so let's go a little bit more about productivity. So here, excuse my very basic drawing. I did it in PowerPoint. But here, okay, so this is an example, okay, because there's so many different sizes and lengths and things like that. So in this case, we use plane wave imaging, okay. Actually, I should specify adaptive plane wave imaging because we could adapt to the surface. We use the swath size that's approximately 5-inch, 127 millimeters. 20-foot billet length, 12-inch diameter is it's an average. There's various diameters. And then, of course, we're doing a 360-degree rotation with a 1 millimeter step along the rotation. So if I assume 80% overlap, which is very conservative, okay, we could probably even look at 95 or 90% type of overlap, okay? But if I did that, we take about 30 seconds, and that's also a conservative number. I think we can go a little bit faster than that, but 30 seconds on one rotation. we get about 30 minutes for this type of billet size. And in some cases, again, it depends because there's so many ways it's implemented in the field. Some cases it could take a few hours to even a day. I've seen people on this inspection. So look at that time saving. I mean, that's incredible. And then this is just talking about a little bit more about just the calibration standard here, where it's a number 2 flat bottom hole, and a little bit more about the noisy grain structure, and the fact that, you know, just because we increase sensitivity doesn't mean necessarily that it'll solve all the problems. You know, we saw that earlier, you know, because if it's very noisy, you can't just increase the gain, because then you'll see more than you want to, right? Okay, so this is also just to explain how the signal to noise ratio is expressed, what in this case. And then this is a drawing of just the flat bottom holes. It's just a typical billet standard. These are starter holes, that's why you see that. So you have all these down here. This was just for fun to put it in a 3D volume to see how we can do that, since you take the full rotation. Just to explain, a little bit about plane wave imaging. Instead of firing one receive all like you would in full matrix capture, we fire all the elements and then receive all of them in individual buffers, and then you can choose arbitrary number of angles, and then when you receive all, what we're doing is calculating like TFM. And the advantage of plane wave, the reason I show this is the fact that instead of, let's say you have 64 element system, that's 64 squared, 4096 raw RF waveforms, but that's to the power of 2. But when you actually talk about plane wave, now we're doing a multiple, right? So it's a multiple of angles, so it's a lot less data. A lot less data means smaller file sizes, and it's easier for storage, easier for the computer, and you can go a lot faster, because let's say we can accomplish that in, let's say, 6 or 7 shots. Even in phased array, if you were to do a linear scan that could, let's say, a 32 element aperture across 128, you would get something like 96, 97 shots. So now you spend a lot less time per position, and that's where you can get some very good speed. Surface adaptive, what we do here is because we're doing things in the full matrix capture style, then we can take the shot in the water, and then once you take that shot, you can redraw the profile, and once we know the profile, we can adjust basically adjust the focusing underneath the material. And this is just an example of what it looks like without any adjustment with TFM, and then here with the adaptive correction. And this profile here, this is what shows us that estimation. And then a lot of times we're asked about near surface resolution, which is of course very, very important. And so here, this is a number 1 flat bottom hole. That's right here. You can see that, you know, if you're not used to this dimensions, it's a 0.4 millimeter diameter, but you can see here we have quite a good margin between the front surface and the indication here. So that's quite a good near surface resolution. This is just another thing that we continue to test based on uniform sensitivity. Of course, you want to be uniform across the vertical and horizontal. And so this is actually a little bit of a video, but for the sake of time, I'll just move past it. And then this one is expressing the depth as we go deeper to achieve the sensitivity that we need across, again, both vertical and on the horizontal grid, which is very important, especially for setting your reject criteria of either using signal to noise or amplitude, or both. We've used some other techniques, namely phase coherence, which is based on phase. I won't go into that in this presentation, but if you come back at the 521 in 118, I'll talk a little bit more about this one. But this is just a very quick one where we took, this was done in a plate, a very attenuative titanium plate. And so here you can see some of the grain noise that can appear. And then here with PCI, it's a lot cleaner. And then that's just another shot of that. Okay, so just in conclusion, so we kind of reviewed over the benefits of these new techniques. Let's see how we can deploy those into this type of inspection, we can see that we can reach good sensitivity, improve SNR, and faster inspection speed. So the next steps really are to continue with, to collaborate with industry. You know, we are the instrument manufacturer, we do some R&D, but we really need to partner and collaborate with industry to be able to improve, you know, to see how can we use this in a real application, how to do more tests to prove out the reliability of this technique. So thank you very much.